So in this continuation lecture, we want to look at the system that we started looking at, which is just this 2-degree of freedom system. This 2-degree of freedom system that has 3 springs, 1 intermediate spring and 2 similar masses. And we calculated the natural frequencies of this 2-degree of freedom system. Now what we want to do is calculate something called the mode shape, and I'll explain what the mode shape is as we go along. Let's look and see what we did before and how does the mode shape come into play, and what is the mode shape. Well, we have a spring system here, 2-degree of freedom, and what we said was we calculated the natural frequencies, 2 natural frequencies for this system, such that in free vibration, if you were to basically just maybe give the yellow mass or the red mass, or even both of them, some initial displacement or velocity, the system vibrates back and forth, and the yellow mass oscillates with a frequency omega 1 as well as omega 2, and the red mass oscillates with a frequency omega 1 and omega 2 as well. Now, for each natural frequency, so for each natural frequency, omega 1 and omega 2, there's a particular shape of vibration associated with each one. So it means that for omega 1 it vibrates, the mass in yellow vibrates with respect to the mass in red in a certain way, and then for omega 2 the mass in yellow vibrates with the mass in red in a different way, right? That is what we call the mode shape, right? And we have a mode shape associated with your first natural frequency omega 1 and your second natural frequency omega 2. How do you find these shapes, right? Well, what we need to do is we need to go back to this expression that we derived earlier, and again this expression is simply, try to get accustomed to thinking about it as being, this expression here is just the stiffness matrix minus omega squared, the mass matrix, right? So this expression in the blue bracket here is just this red equation here. So we had this expression multiplied by x1, x2 is equal to 0, where x1 is the amplitude of vibration of the yellow mass and x2 is the amplitude of vibration of the red mass. So we had this expression. Now we use this expression to calculate the natural frequencies. We said, well, the determinant of what we have in blue here is going to lead us to the natural frequencies, and we did that, and we calculated omega 1 squared as k on m and omega 2 squared as 3k on m. But those mode shapes that we just spoke about can also be determined from this expression. It can be determined from this expression. Well, how do we do it? How do we calculate the relationship or between x and 2, or the mode shape of the vibration? Well, we say this. You select a particular row that you're interested in. Now, I'm going to select this row, right? I want you to be confused with this because k minus omega squared m is really the entire thing in blue, right? So anyway, so we select this row here, and then we multiply it by this this column here, right? So what am I going to get there? This is to calculate the mode shapes. We're going to get 2 k minus omega squared m multiplied by x1 minus k x2, which is equal to 0. Now that we've done that, I can see, well, what does this expression look like if omega 1, if omega is equal to omega 1, or omega squared is equal to omega 1 squared. Meaning that I want to substitute the first natural frequency for omega here. Alright, what does that expression look like? Well, that expression looks like 2k minus omega 1 squared is just k on m multiplied by m x1 minus k x2 is equal to 0. And you can recognize that this just becomes k x1 minus k x2 is equal to 0, or x2 is equal to x1. Now, when we talk about mode shapes, we are not talking about exactly determining what capital X1 is or exactly determining the value of capital X2. Those things can only be obtained if you have the initial conditions of the system. But rather, when we are talking about mode shapes, what we are now talking about is what is the ratio between X2 and X1. Now, it's very clear that I can represent this ratio in a way that says, well, X1, X2 for omega 1, and I'm going to just put that 1 there for the first natural frequency, or this is known as your first mode shape. I'm going to say, since I'm only interested in relative amplitudes, I'm going to just say, what if x1 was 1? Just arbitrarily, what if x1 was 1? Well, x2 would be equal to the same thing, it's 1. And that's what the first mode shape is. One way I can represent that, and we'll go to the physical significance shortly, but this is your first mode shape. One way I can represent that is I can say, well, if I had a graph and maybe this was amplitude, on the y-axis, and down here maybe this is the mass associated with the yellow mass, right, which is I'm just going to call it the first mass, which is the yellow mass, and then I'm going to say, well, the second mass, which was the red mass, is here. I'm just going to call that 2, just so that you know it's the yellow mass and the red mass that I've plotted here on the x-axis. I can represent that mode shape very simply by saying this. I can say that this end I'm going to consider it fixed. Why do I consider it fixed? Because if you looked at the diagram, it was fixed on this end here, and this is the yellow mass here now. When x1 is 1, you'll have a value of 1 here. And when x1 is 1, which corresponds to this value, x2 associated with the red mass is also 1. Look at this as x2 here. And then we have another fixed end across here. And the fixed end just means that there is no displacement, right? So, draw that back. Why the fixed end? Because you remember from the question that this is a fixed end here as well. So this is how you represent the mode shape graphically. Now, what does it mean? What does it mean if when x1 is equal to 1, x2 is equal to 1? Well, what that tells me is that the vibration of the first mass in yellow oscillates in exactly the same phase as the mass in red. It means when x1 sees a maximum, x2 also sees a maximum. When x1 sees a minimum, x2 sees a minimum. So how does that look? Now again, this only corresponds to the vibration of the masses with frequency of omega 1, your first natural frequency. Your first mode shape corresponds, and this point should be emphasized, your first mode shape corresponds to your first natural frequency. Corresponds to first natural frequency. How does it look? Well, let's look at this little animation that I have here. This is an example of how it oscillates, and I'm just going to show you. You can see the first mass and the blue mass, first mass and the second mass, what we had as yellow and what was red here, oscillates in sync or in phase. And that's what it means. When this sees 1, this sees 1. When this sees -1, this sees -1. So that's what it means to oscillate in phase. And you can see that how the displacement of both vary there. This blue line is meant to show the displacement of both the first mass here and the second mass here. So that's what actually happens. Now let's look at the second mode shape. What does the second mode shape correspond to? Well, the second mode shape corresponds to the second natural frequency, right? So to do that, I again go back to this expression that I multiplied this row, the first row, by the first column. And remember, I had this expression, right? So what I want to do now is, when I multiply that first row by that first column, I'm going to bring that equation down. So I've brought this equation a little bit lower down. And now I want to say, well, I'm interested in the second mode shape, or when omega is equal to omega 2, or omega squared is equal to omega 2 squared. Well, what does that mean if omega squared is equal to omega 2 squared? It means omega squared is going to be equal to 3k on m. That was the second natural frequency, right? Remember, omega 2 squared was that? Yeah? So I want to substitute 3k on m into this expression here. So now I'm going to get 2k minus 3k on m is just going to give me 3k x1 minus k x2 is equal to 0. And then I'll say, well, this is just minus k x1 minus k x2 is equal to 0, or minus x1 minus x2 is equal to 0. And now what I'm saying is that, well, x2 minus is equal to x1. Before, what did we have? We had x2 was equal to x1. Now I'm saying that for the second mode shape, minus x2 is equal to x1. What does that mean? It means, therefore, that again, if I'm interested now in the second mode shape, and let me be clear, so it's the second mode shape, and what does it? It corresponds to omega 2. Then it means if I have x1, x2 again, that is going to be equal to, if I let x1 be equal to 1, and I should put a subscript 2 here just to show you the second mode shape. If I have x1 is equal to 1, what does x2 equal to? It equals to minus 1. Right? It's easy to see because obviously if I made x2 the subject of the formula here, it would have been minus x1, right? So if I let x1 be equal to 1, x2 is going to be minus 1. How do I represent that in that same graph that I drew? Well, I can say, again, on my y-axis I have amplitude, x-axis I have where the mass is located. So First mass was yellow. Had this M1 here. Second mass was red. This M2 here. And now what I'm saying is that when x1 is 1, that didn't change. This is just relative amplitudes we're looking at. When x1 is 1, then we start from the fixed point here, go up to 1. But then we're seeing that x2 is minus 1, so now I need to come across here and I need to find minus 1 on the side here. Maybe minus 1 falls somewhere here, right? So we draw to connect 1 to minus 1. And what does that minus 1 connect to? That minus 1 connects for x2, right? Then it goes back up to being a fixed position. And this is how the second mode shape looks. This is the second mode shape. This second mode shape moves from x1 equal to 1 to x2 is equal to minus 1 here. At this point where it cuts the 0 axis, you know what they call this? Remember, this was a fixed point here and this was a fixed point here. So if it cuts the 0, it cuts the axis here, it means the amplitude is 0. We call this point a node. A node is a point where there's 0 amplitude, doesn't oscillate. When we had x1 as capital X1 as equal to 1 and capital X2 as equal to 1, right? For the first mode shape, we said, well, both of them were in phase when x1 saw a maximum, x2 saw a maximum. Now when we are seeing that x1 is equal to 1, x2 is equal to minus 1, that's what we're seeing here for the second mode shape, it means that the vibration is completely out of phase. So when x1 sees a maximum amplitude, x2 sees a minimum amplitude. What does that mean? And minimum in the negative sense, right? What does that mean? Well, let's look at a graph of how it would oscillate in the second mode. Remember, it's oscillating at omega 2. How does it oscillate? Do you recognize what happens? It's basically completely out of phase. When the first mass here to the left is at its most to the right, so it has been displaced to the most to the right hand side, do you recognize the blue mass is most to the left hand side? So when this mass has its maximum positive displacement, this mass has its minimum negative displacement, and vice versa. Now the important point to also look at is, remember, we got a point that was at a node, right? We got a point that was at a node here at the center. Well, what do you think is the node here? Well, a node is a point of 0 displacement. What do you think is the node here? What do you think is the node here? Well, do you recognize that here is fixed and here is fixed? But also it seems like in the middle of the spring here, the middle of the spring doesn't move. The middle of this basically moves back and forth relative to the middle of the spring. This moves back and forth relative to the middle of the spring. The middle of the spring is the node, and that's the same node that we had in the graph before. You look at this here. Was there any node here? Was there any node here? Right? No, there was no node. There weren't any nodes then. We're not going to consider the fixed end nodes, right? Because these were actually fixed due to the boundaries. In the vibrating system, there are no nodes. It moves back and forth. There are no points in this vibrating system where the amplitude is always 0, right? And again, other than the fixed ends, but we're not considering those, right? But those are more boundary conditions. So that's basically what the mode shapes mean. Now, just to summarize, what I'm telling you is that these mode shapes give us an idea that how the shape of vibration is for each natural frequency, right? So when these masses oscillate with an omega 1, then they basically oscillate in phase with each other. And when these masses oscillate with omega 2, they oscillate out of phase. Now, we go back to these diagrams, and you must recognize something. What we've done is we've looked at them separately, this omega 1 separately from this omega 2. But when in the real system, what actually happens is that this does not vibrate with omega 1 and then starts to vibrate with omega 2, or this doesn't vibrate with omega 2 and then start to vibrate with omega 1. No, it's a combination. It's a combination of this mode shape plus this mode shape. It's a combination of this mode shape plus this mode shape. So really what actually happens is that the total vibration is going to be, to a certain extent, the sum of how this vibrates with how this vibrates. The actual displacement is going to still depend on your initial conditions. So the initial displacement of mass 1, the initial displacement of mass 2, or the initial displacement of M1 and the initial displacement of M2. That's the actual displacement. This just gives us an idea of how the relative vibrations occur for the particular natural frequencies, and we will be looking at some of those initial condition type problems. Now, one of the key questions you should ask is you should go back to this equation that I got the mode shapes from, and you should ask, well, why did I take the first row and multiply it by this column? Why didn't I take, for instance, the second row? Why didn't I come across here, and why didn't I take the second row and multiply it by this column? Well, the answer is this. You could have taken this second row and multiplied by this column and work with that equation instead, and got the exact same answers that we would have gotten by taking this first row and multiplying by that column. So you can try that one on your own. You can use this column and multiply it by x1, x2, and still get the same mode shape of x1 is equal to, when x1 is equal to 1, x2 is equal to 1. And then when x1 is equal to 1, x2 is equal to minus 1. You would have gotten the same thing.